Good morning and welcome. Why are trees so romantic? It's because they're really, really sappy. Get it? Trees have sap. All right. Speaking of trees and beautiful segues, today we are talking about probability tree diagrams. And I like to coin the term probabilitrees. Okay. We use these for simple and complex scenarios, especially we use it for advanced and standard, but in standard, we see this almost for any probability question. I can almost 85% guarantee it'll be a tree. Okay. The way that these trees work, I think we've touched on this before, but each stage of branches represents a single event. Okay. So for example, let's do this. That's event number one. That there is event number two. And I'll pick another one. That there is event number three. Okay, so I'll write this down. This is how a tree works. Okay, so those are your different events. They line up on the vertical. Okay, now the other thing to note here is unique probabilities. Because usually when we see true and false, they're generally 50-50. So if it's 50-50, we don't have to label anything on the branches. However, if we have unique probabilities, they're supposed to be labeled or listed on each branch. So for example, you can see here that the probability of A is 2 on 3, probability of B is 2 on 3, 1 on 3, 2 on 3. And then for the next part, the second event, C and D, probability of C is 2 on 5, probability of D is 3 on 5, blah, 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 so on and so forth. Now, a couple things to note and why we list these things out on branches. The way that we find the probability of compound events is found by multiplying the probabilities that it's kind of made up of. So for example, if I wanted to find the probability of AC, that means A and C, I would multiply those two together. So that means it'll be a third times 2/5. And if you've forgotten, which if you're my class, some of you guys would have, the way that we multiply fractions is either A, use a calculator, or B, numerators with numerators, denominators with denominators. So in this case, 1 times 2 is 2, 3 times 5 is 15. So the probability for this particular case in getting an A and then a C is 2 on 15. Same thing for AD, it'll be a third times 3/5. BC would be 2/3 times 2/5. Hopefully you're tracking along and seeing where I'm pulling out these numbers from. And then BD is 2/3 times 3/5. Okay, now if I calculate these really quickly, 3 on 15, 4 on 15, 6 on 15. Okay, now mathematically, 2, 3, 4, and 6 add up to 15. So that means these all add up to 1. Now that's what I'm talking. It says each branch, so each little kind of like that thing should always add up to 1. So a third plus 2/3 is 1. And 2/5 plus 3/5 add up to 1. That's the idea that each branch, so it could be like a three-way branch, it could be a four-way branch, but each single kind of like section should always add up to 1. Okay, now let me show you how that might look like in a question. A couple things to note here is we have to be extremely careful if the question is with replacement or without replacement. Now, sometimes it means we take something out and then we put it back in. So your probability of picking again would be the same. Or sometimes if we take two things out, once we've taken something out, it changes the probabilities of what's left. Let me explain. So in this question here, it says a bag has 6 red and 3 blue counters. And then a person reaches into this bag and picks 2 counters at random. And we want to draw a probability tree diagram to represent this. Okay. Now, if I'm picking 2 counters, okay, that's where it doesn't sound like it. But if maybe pick 2 would be what I highlight. So if I say pick 2, what I want you guys to think of is that there is your hint that it's a multi-stage. And your multi-stage is your hint that even if I didn't say draw a tree diagram, sometimes the tree diagram is the safest bet to take from here. Okay, so if I pick two, or if I, two things happen, those are my two events, that's my multi-stage. Okay, now also in this particular case, if I pick two, it's not like I take one, put it back, take another one, it's at the same time. So this is what we call without replacement. So you can see in this question, these two words, picks two, okay, kind of implies a lot and kind of like sets the basis for our question. So I'd be highlighting these things. Okay. Now let's draw a probability tree. Now, if I was to pick a counter, my two options are it's either going to be red or it's going to be blue. Okay. And for my second pick, it's either going to be red or it's going to be blue. There are no other options. Okay. Now, what we need to do though is these, I'm not, okay, timer. I'm not going to leave these blank because the probabilities of me getting a red or a blue, they are not even, they are not 50-50. Okay, so I look here, the probability of red is there's 6 out of a total of 9 counters because 6 plus 3. Okay, so the probability of blue is 3 out of a total of 9. Okay, now if I've picked one red, I started with 6, I picked one red, I put my hand back in the bag, there's no longer 6 red tokens for me to pick. There's only 5 left. So there's only 5. And this is where most people slightly forget. It's not out of 9. Because if I've started with 9 counters and I've taken one out from the first pick, there's only 8 left. So with replacement, we need to make sure that we account for this. So now there's only 8 left of the red. Now I haven't picked any blue. And we also remember that this branch here needs to add to a total of 1. Okay, so that means there's still 3 blue counters. That makes complete sense to me. 3 out of 8, that's the probability of getting blue. Okay, now the temptation is to copy and paste these numbers and put them down here. But you got to remember, if I take this route here, I've taken a blue, I should still have 5 red, right? And it will not 5 red, sorry, 6 red. Whoops. I did what I said I shouldn't do. Because there's 6 red ones left because I haven't picked any. And then because I picked 1 blue, there's only 2 out of the 8 that are left. Okay, and this is how our probability tree diagram should look. Okay, we've got our trees, we've got our 2 events, the 2 counters, and we've also got the correct probabilities on each tree, and we've accounted for not replacing whatever we picked on the first event. Okay, now here are some examples of some questions that may come from it. Find the probability that I pick both red. So for me, it's going to be, I'll just write it as PRR for double red. And the way that we do that is I just go, okay, well, red is 6 on 9 times 5 on 8. So those are the 2 probabilities. I multiply them together, and that gives me, should I simplify for you guys? Yeah, I should. 15 on 36. I think I can do better than that, actually. 10 over 24. What? Okay, 6 will go into it. So this is just, you can put it in the calculator. 5 on 12 is the simplified version. Now, if I ask for the probability of 1 blue, 1 red, it's actually asking for 1 red, 1 blue, or blue and red. Okay, so it's one or the other. So for this particular case, red, blue is 6 on 9 times 3 on 8. Okay, there's the first one. What we need to do is we also need to plus the blue, red. So blue and red is 3 on 9 times 6 on 8. Okay, now this one here, you can put in your calculator. I'm just doing the math here. It's actually half. 18, hold on. 18 plus 18 is 36 on 72. Yeah, it's half. Okay, simplified, you put that in your calculator, it comes out with a half, okay? Put it in your calculator, double check for me. And the last one, probability of at least. Now, at least, if you remember from last lesson, is, Cripplet, is probably the biggest hint that it's a complementary question. The easiest to go P at least one blue is the opposite of at least one blue is they're all red. So I'm just going to go probability of, or one minus the probability of red. Red. Okay. Now, if that's not making sense, pause the video and try to make sense of it. Why is at least one blue the same thing as one minus? It's like it's the complementary is all red. Because if it's not all red, that means at least one of them is blue. Okay. A little bit confusing. See if that makes sense to you. Now, if you have at least one blue, probability of one minus double red, it's just going to be one minus 5/12. And in this particular case, it's just going to be 7/12. Okay. And that there should be your answer. Hope that helps. Good luck, all the best, and I'll catch you in the next one. All right, bye.